Bismillahirrahmanirrahim. So let's see this problem. A pump steadily draws water, so you have water through a pipe from a reservoir at a volumetric flow rate of this. So we have the volumetric flow rate equal 1.3 liters. We have water, okay, and we have a pump. So at the pipe inlet we have pressure P1 equal 101.4 kilopascal. So it's atmospheric pressure, and T1 equals 18 degrees centigrade. The velocity V1 equals 3 meters per second. Okay, the pump exit pressure is P2 equals 240 kilopascal. The temperature T2 equals again 18 degrees centigrade, and the velocity V2 equals 12 meters per second. The pump exit is located 12 meters above the pipe inlet. So if we draw the pump like this, okay, and so this is here like that. So this is the outlet, and this is the inlet. This is 1, this is 2. So the difference in the height is 12 meters. This is pump. So we have Z2 minus Z1 equals 12 meters. Okay. Determine the power required by the pump, okay, in kilojoule per second or kilowatt. So we need what is the power required by the pump. So it's how much power the pump should give the water, okay, because we give the power, the pump electrical power, and then the pump motor will give the water the power in order to be pushed, okay, and to increase the energy of the water. So let's write the energy equation. So you have Q dot minus W dot plus M dot. Again, this is one inlet, one outlet, so we can just use this form. So M dot H1 minus H2 plus V1 square minus V2 square over 2. And let's write this 2000 because we'll have H in the enthalpies and everything else here with in kilojoule, plus G Z1 minus Z2. Okay. So this is what we and of course this equals to 0, and of course here also what we'll have is that we need also to divide by 1000 because this will give us in kilojoule, in joule. So we need to divide by 1000 to have it in joule, in kilojoule, sorry. Okay. Here we say that to ignore the heat transfer, therefore Q will be 0. We need to find what is the power. So the power will equal just this. Now we need M dot. Okay, m dot times, and we have the same thing, the all of this here. M dot, okay, we have the volumetric efficiency, so divide that by V. But here we need to know, for example, the inlet and the outlet. Since it's pump, then we know it's water, but just to make sure and to practice again. So if you go to table A2 and for the temperature of 18, so this is table A2 and temperature 18 degrees centigrade. We see that the saturation pressure, okay, is 0.002 bar or 2 kilopascal. So this is 2 kilopascal, but we have our pressure here at the inlet is 101 kilopascal and at the outlet is 240. So in both cases it's very clear that what we have here is water. And for water, for the compressed liquid, V is simply can be approximated to be Vf at the temperature, so at 18 degrees centigrade, and that from the table at 18 degrees centigrade, this is V, and we don't forget that this is already multiplied by 1000, so it's 1.0014. So V equals Vf at 18, and this is 1.0014. صح؟ أيوة صح. زين times 10 to the power minus 3 cubic meter per kilogram. So this is Vf, and therefore we can get what is m dot using this V. And for H1 and H2, okay, we have H again can be approximated to equal HF, but we said that to be more accurate, H equal HF plus Vf P minus P sat of 18 degrees centigrade. Okay, and this will be applied for points 1 and 2. Okay, so this is H1, and here will be P1, and for H2 is the same thing, but what we'll have here is P2. So H1 minus H2 will equal HF plus Vf P1 minus P sat minus HF then minus Vf, okay, because here the bracket, P2 minus P sat. HF will be cancelled with this one, and Vf P sat will be positive there, and this will be cancelled with this. Then what will be left is that Vf at 18 degrees centigrade times P1 minus P2. This is H1 minus H2. Okay, so we substitute this here in the equation. We have V1, we have V2, we have Z1, we have Z2 minus Z1. Okay, so Z1 minus Z2 will equal minus 12. So Z1 minus Z2 equals minus 12 meters, and the rest will be just calculations. Okay. The next problem is this one. So we have again a refrigerant 134 air, enters a heat exchanger at this temperature and quality, and exits a saturated vapor at the same temperature. And separate stream of air enter. So if we draw the heat exchanger, of course this is just a sketch, so it doesn't really represent the actual heat exchanger. Okay, so if we see that this is the refrigerant, and we'll give it so 2, this is R134A. So we have T1 equals the entrance minus 12 degrees centigrade, X1 equals 0.42, okay, and exits a saturated vapor, so at the same temperature. So T2 equals again minus 12 degrees centigrade, and X equals 1, saturated vapor, with the volumetric flow rate of 0.85. Okay, so we have the volumetric flow rate and exits a saturated vapor at the same temperature with the volumetric flow rate of this. So this is V dot 2, okay, equals 0.85 cubic meter per minute. Okay, you should be careful with the volumetric flow rate, because if you have compressible substance, then we need to know where is this flow rate. Is it at the inlet or the outlet? Here it says and exits a saturated vapor at the same temperature with a volumetric flow rate. So this is at the exit. So this is for the refrigerant. Then we have ideal gas air. So this is air, and we call this 3, inlet of air, and the outlet is 4. It's very important to sketch this and show the numbers. So for air enters as this, so T3 equals 22 degrees centigrade with mass flow rate. So we have the mass flow rate of air, okay, equals 188 kilogram per minute, and exits, so T4 equals 17 degrees centigrade. Assuming the ideal gas model of air and ignoring kinetic and potential energies, we need to know the mass flow rate of the refrigerant. So M dot R in kilogram per minute. We need to use this to find it in this unit. The heat transfer between the heat exchanger and its surrounding. So that means that there will be heat transfer either in or out, okay, we don't know, in kilojoule per minute, so Q dot. Okay. So here we have two substances, the refrigerant and this. We need Q dot of all heat exchanger. So our control volume will be the whole heat exchanger. So this is our control volume. Okay. So if we write the energy equation, Q dot minus W dot plus, now we have summation, okay, and here the kinetic and the potential energies are not there, so we are only left with, so N M dot H minus summation of outflows of M dot H equal 0, because now the velocity, the kinetic and the potential energies are not there. So we have only the enthalpy. There is no work, so this is 0. So Q dot equals summation of out, because these will be taken to the right hand side with negative sign, m dot h minus summation of inlet flows of m dot h. And what we'll have, the outlets are 2 and 4, so m dot 2 h2 plus m dot 4 h4 minus m dot 1 h1 minus m dot 3 h3. Okay. Of course here 1 and 2, so m dot 1 equal m dot 2 equal mr, and m dot 3 equals m dot 4 equals m of air, m dot air. So 2 and 1, this is a refrigerant, so mr h2 minus h1, and 4 and 3, this is ma, so h4 minus h3, outlet minus inlet. So now it's straightforward. We only need to find the enthalpies and we can use the tables. So for this one, state 1 for the refrigerant, minus 12 and 0.42, we go to the property table of the refrigerant. Again, make sure that you use the right table, and we have temperature of minus 12, right? Yes. So minus 12. Okay. We have here the volumetric flow rate. Therefore, m dot. Okay. Yeah, but this is at the outlet. So m dot equals v dot 2 over v 2. Okay. But in 1 we can get h1. So h1 this one, okay, h1 equals 34.39 plus x, which is 0.42, times hfg, which is this one, times 205.77. So this will give us h1. h2, okay, is at the same temperature with x equal to, so this is h2 is simply hg. So h2 is simply hg, saturated vapor, so 240.15 kilojoule per kilogram. So this is h2 for the refrigerant, and v2 equals vg, and that's 0.1068 cubic meter per kilogram. So we have this, and now we can have what is m dot r. So that's about the refrigerant. Now, so we have m dot r, h2 and h1. m dot a is already given, okay. All what we need is to find h3 and h4 using, again, we can use the air tables. So T3 equals 22 plus 273, this is 295 Kelvin. T4 equals 17 plus 273, this will equal 290 Kelvin. So we need for 290 and 295, we go to the air table, and 290 is this, and this is H, and 295 is this one, and this is the enthalpy. So this is H3 and this is H4. We can use again for air CP. Right. So for air, we H4 minus H3, we can say that this is CP T4 minus T3, and then we need to find the average of the CP at the average temperature, which is at 292.5. So we need to again we need to do some interpolation. But in this case, it is easier to use the air tables. So these two can be easily found, and therefore we can calculate what is Q. Thank you.